Hey everyone, and welcome to this explainer. Today, we're doing something really cool. We are going to unpack the brilliant engineering required to safely harness the power of an atom. We're essentially going to build a nuclear reactor from the inside out, looking strictly at the fundamental physics and the design requirements that make these incredible machines even possible. But before we start building, we have to ask ourselves a pretty massive foundational question, right? How exactly do you take a fundamentally chaotic, microscopic atomic process and turn it into a highly controlled, massive, clean energy engine? Well, it takes a very specific combination of materials, all working together in absolute perfect harmony. So here is the blueprint we'll be following today. First, the core, which is our fuel. Second, taming neutrons with a moderator. Third, extracting power using coolant. Fourth, containing leakage with a reflector. Fifth, safety and throttle through control. And finally, the skeleton or structure. Okay, let's start right at the top. Number 1, the core, fuel. Now, selecting the right fuel, it's not just about, grabbing a chunk of uranium and calling it a day. It actually requires this highly precise mathematical balance between different types of nuclides, and that all depends heavily on the energy environment of the reactor itself. And the ultimate gatekeeper concept here is what we call the fission-to-capture ratio, or simply F/C. For material to even qualify for selection as fuel, this energy-dependent ratio absolutely has to be greater than 1, or unity. If it's less than 1, well, the material just absorbs more neutrons than it produces through fission, and the whole reaction just kind of dies out. Which brings us to a really fascinating balancing act. See, fissile nuclides clear that F/C hurdle in both the thermal and fast ranges, but fertile nuclides fall short. That means fertile materials literally cannot act as fuel on their own. So engineers have to cook up this exact recipe, carefully mixing the two together. If you're working with low energies, you just need a low fissile fraction. But if you're operating in that high energy fast region, you're going to need a high fissile fraction, specifically greater than 10%. Moving right along to step 2, taming neutrons. Moderator. So this need for a moderator introduces a huge fork in the road for reactor design. If you're building a thermal reactor, you absolutely need a moderator, something like heavy water, light water, graphite, or beryllium, to intentionally slow those fast-moving neutrons down. But if you're building a fast reactor, you actually rely on those high-energy neutrons, meaning you skip the moderator entirely. That brings us to number 3, extracting power. Coolant. Think of the coolant a lot like the radiator fluid in your car, right? Its main job is to extract the fission energy being produced. But in a nuclear reactor, it has to hit a very specific checklist of properties. It needs great heat transfer capabilities and favorable chemical traits for sure, but crucially, it has to be neutronically acceptable. That means it needs small absorption cross-sections, so it doesn't accidentally swallow up the very neutrons we desperately need to keep the whole reaction going. So the real takeaway here is that your choice of coolant is entirely dependent on the reactor path you chose earlier. For a thermal reactor, you're typically going to use light or heavy water. But for a fast reactor, the go-to choice is actually liquid sodium. Pretty wild, right? Okay, let's jump to number 4, containing leakage, reflector. In literally any reactor, you're going to have some neutrons trying to escape the core. It's just bound to happen. To prevent this neutron leakage, engineers install a reflector right around the core. It's made of specific materials like nickel or aluminum, and it acts almost like a funhouse mirror, bouncing those escaping neutrons right back into the fiery center. And this is a total game changer, because retaining those neutrons actually lets engineers shrink down the overall size of the core. Next up, number 5, safety and throttle. Control. Now, an absolute non-negotiable requirement of any reactor design is having a foolproof way to control its performance. Because without that, you don't have a power plant. You just have an unguided, dangerous reaction. To pull this off, we use movable control rods. You can think of these as your ignition, your gas pedal, and your brakes all rolled into one. Operators use these rods for 3 core actions: starting the reactor up, adjusting the rate of power production on the fly to meet our energy demands, and of course, shutting the reactor down safely whenever needed.
But what's really interesting here is the material science. These rods are usually forged from stuff like boron or cadmium. And why is that? Well, unlike our coolants or structural elements, we actually want these materials to aggressively absorb neutrons. When you plunge them down into the core, they soak up the neutrons like a sponge, starving the reaction and bringing the power levels right down.
And finally, number 6, the skeleton, structure.
You can think of this structural skeleton as the true unsung hero of the whole reactor. It serves a bunch of heavy-duty purposes. It acts as the protective cladding that physically holds the nuclear fuel. It forms the intricate piping for the coolant, the guide tubes for our control rods, and ultimately it serves as the massive outer reactor vessel that supports every single component we've talked about so far.
Because they're sitting in, let's face it, one of the absolute most extreme environments on Earth, these materials face two massive hurdles. First, they have to be neutronically compatible, meaning they can't interact with neutrons in a way that hurts the reactor's performance. And second, they just have to survive intense, incredibly high temperatures for prolonged spans of time without degrading.
So to achieve this superhuman feat of engineering, reactor designers usually lean on a select group of super tough, reliable metals. Zirconium, aluminum, and stainless steel are the most common structural materials used to build out these frameworks and pipings, ensuring the whole system stays completely contained and, most importantly, safe. When it comes down to it, as this quote beautifully summarizes, there is just no one-size-fits-all approach to building these incredible machines. Every single material choice, their composition, their quantity, whether you go with heavy water or sodium, boron or cadmium, it is all strictly dictated by the specific type of reactor and the precise amount of power it's designed to produce. It's literally a giant, highly customized puzzle. Which leaves us with a pretty fascinating thought to wrap up this explainer. We've just seen how perfectly balanced today's reactor designs absolutely have to be, juggling fuel chemistry, extreme heat, and neutronic limits. So, as we keep pushing the boundaries of clean, limitless energy production, how will the materials and designs of tomorrow evolve to master this incredible atomic recipe? Thanks for exploring this blueprint with me today. Keep asking questions and keep learning.